Eco हो रहा है तो Yes, sir, we can start. A very good morning to all of you for the third day of ATAL FDP program. I welcome Professor Vasant Matsagar. He is professor in Indian Institute of Technology, Delhi, and his expertise is in multi-hazard protection of structures, earthquake, wind, blast and fire engineering, structural engineering, earthquake and wind engineering, offshore structures, fiber reinforced polymer composites, finite element analysis, and blast and fire engineering. Sir has received. आप leave कर दीजिए, leave करो. Sir has received the CDRI fellowship. Sir has also received a prestigious fellowship for the research, Ambert Research Fellowship for the Experienced Engineers, Alexander Worm Albert Foundation. Sir has also received the Teaching Excellence Award by Indian Institute of Technology, IIT Delhi. Sir has also received the DST Young Scientist Award by Science and Engineering Research Council at Department of Science and Technology, DST, by Ministry of Science and Technology, Government of India. He has also received DAE Young Scientist Award by Board of Research in Nuclear Sciences at Bhabha Atomic Research Center, Department of Atomic Engineering, Government of India. Sir has also been awarded with the DART Award for the study visits to German universities under the Faculty Exchange Program. Sir is also a DART Research Ambassador for the German Academic Exchange Program. Sir has also received IBC Award for Excellence in the Built Environment of Indian Building Congress by Mr. S. Jaipal Reddy, Union Minister for Urban Development, Government of India. Sir has also received the Indian Institution of Engineers IEI Young Engineers Award and also Outstanding Young Faculty Fellowship by IIT Delhi. Sir has delivered various expert talks in conferences and various training programs at national and international level. Sir has published number of patents and various research papers in journals and conferences. Today's topic for the expert talk is vibration control system for earthquake resistant design. On behalf of Department of Civil Engineering, University Institute of Technology, RGPV Bhopal, I welcome you, sir, for the ATAL FDP program.
Good morning once again. Is my screen visible?
Yes, sir.
Are you able to see my presentation?
Yes, sir.
Okay. Thank you, Dr. Aruna, for the nice introduction. Good morning to one and all.
So there are nearly about 127 participants all over the India who has registered for this FDP program.
Very good. Okay, so I'm glad to know that there are a large number of participants who have interest in earthquake resistant design and construction practices being delivered through the AICT sponsored ATAL FDP organized by Dr. Aruna Rawat Gupta. So in this FDP, I will be having two presentations made. Today is the first presentation on vibration control system for earthquake resistant design today. And tomorrow I will be focusing more on the a case study of using base isolation systems in one of the real life building projects being constructed. Already it is in use here in Delhi. Therefore, though vibration control systems include base isolation, in today's presentation, I will exclude it from my presentation and I will cover that in tomorrow's lecture. So today I will focus on the other vibration control systems used in the earthquake resistant design. So my presentation will revolve around introducing the basic concepts in dynamics. Of course, I will not be able to spend too much of time on that, but whatever are the essentials from structural dynamics that are used in structural response control, I will quickly touch upon that so that we remain familiar with some of the terms used in structural response control. Then I will move on to the passive, active, semi-active, and hybrid response controls, and then smart dampers and other damping devices, and how we add the artificial damping in the structure in order to reduce down the dynamic response. And then I will talk about some of the algorithms or flows available for the semi-active response control devices and some control algorithms, though due to paucity of time may not be able to cover all the control algorithms, but I'll just give a glimpse of how these control algorithms are used for seismic response control of structures by using semi-active dampers. Am I audible clearly, and are my slides clearly visible, Dr. Gupta? Anyone please confirm if I am audible clearly and my slides are properly visible.
Yes, sir. The slides are visible and you are audible also.
Okay, thank you. So as Dr. Gupta has mentioned during my introduction, I work in the area of multi-hazard uh, response and mitigation of the response. When I say multi-hazard, I essentially deal with the natural hazards and man-made hazards that a particular structure experiences during its service life. For example, if we have considered service life of 100 years, then during the period of that 100 years, it may get exposed to some wind-induced loading, some possibly accidental loading because of the blast, and again blast-induced ground motion, as well as some accidental load, which is either because of man-made or some errors being made by human beings in the form of fire exposure to the structure. The coastal structures may be subjected to tsunami loading. But in all this, almost invariably, all the structures are exposed to two natural hazards, and those two are wind loading and the earthquake loading. So in today's presentation, I will be focusing only on the earthquake loading because that is most prominent, especially in the Indian peninsula. Most of our regions in India are earthquake prone, and thereby we need to have our structures designed in order to cater for the seismic forces induced in the structures. No doubt, equally important is also the wind imparted, and therefore I will, while passing through the concepts of structural response control using earthquake, I will keep on giving you some references to wind response control as well. In case of wind, we divide into two parts. I'm still not going into the time history analysis, but the two parts that I'm saying are one, the ambient wind condition, and second is the extreme wind loading condition when there is some wind storm. So typically we always talk about the windstorm. However, for the serviceability conditions, we need to also control the response of the structure, which is called dynamic response control, under the action of ambient wind as well, especially when the structures are tall. It means when the structures are flexible. It also means when the time periods of the structures are longer. So, with that backdrop, I will start talking about the essentials of structural dynamics that are used in structural response control, and then gradually move towards the structural response control devices and their functioning. However, before going that, I would also like to mention here clearly that these dampers or these devices are used in the structures not only for controlling the response against earthquake induced vibrations and wind induced vibrations, but even for the ambient loading conditions as well. What are those ambient loading conditions? For example, when there are some construction activities going on, there is a possibility that the structure experiences some ambient vibrations. Or in otherwise case, when there is a metro tunnel passing below this building, there is a possibility that the building experiences some vibration when the metro train is passing by. Or if there is a heavy vehicle passing through in a nearby highway, that there is a possibility that the structure experiences some vibrations, and these are mostly ambient. These are mostly called ambient vibrations. So in addition to controlling the response of the structure against the devastating earthquakes, it is also important to control the response. Control means to minimize the response amplitude against these kind of ambient vibrations also. I have already talked about the windborne ambient as well as windstorm conditions and the earthquake conditions. Apart from that, I have also talked about some of the construction activities or transport activities that goes around which may cause vibrations in the structures. Apart from that, there could be some industries surrounding that, and the machineries there may cause some vibrations either from the surrounding parts or within the structure itself. There could be some machine place, like for example some generators or the diesel generators, and they may also cause some vibrations, and these devices may cater for some of those forces which are induced on the structure because of these other different kinds of sources of excitation. So we categorize our excitations in a different manner, and then we write the governing differential equations for the dynamic equilibrium of the structure that essentially contains the mass components, the damping components, and stiffness components. I'm still not at the matrices. I will talk about them in a little while. However, essentially in most of the structural dynamic analysis and design, we deal mainly with these four matrices or these four kind of forces, and those forces are inertial forces, damping forces, elastic or stiffness forces. These days we do not call them elastic forces because we may have some inelasticity as well. And then on the right hand side of the equation, we have the excitation forces. Now, within this, the mass and stiffness are typically explicitly known. What does that mean? It means that we can calculate mass of the structure by just taking the volume multiplied by density. Stiffness is also explicitly known. It means we can calculate the stiffness based on its material and geometric properties. For example, if it is a column, then we know the cross section of the column, and then if it is a rectangular cross section, then using the moment of inertia of, let's say, bd cube by 12, and its length, whatever length that it has, depending on what boundary condition it has, whether fixed pinned and so on, and what modulus of velocity is it has, we can explicitly calculate the stiffness and subsequently the stiffness matrix. So both mass matrix and stiffness matrix can be calculated either by using the continuum approach or by using the discrete approach or by finite element approach, so on and so forth. However, here there are still some approximations being made, particularly in terms of the mass. We are considering that the mass is lumped at some locations, and that approach is called lumped mass approach, whereas there is another counterpart approach which is continuum approach or finite element approach, in which mass is distributed. It has direct implication on the way the mass matrix is obtained. In this case, typically the mass matrix is diagonal one. If we consider the lumping, it means there is no interaction or there is no coupling between the response quantities only insofar as the mass is concerned. Obviously, there will be coupling in the stiffness matrix and the damping matrix. However, from this, our focus remains mainly on the damping, though please note that in structural response control, we do play with the mass and stiffness, and that playing is something that we are really interested in. Now, coming specifically to the damping, which is more important in dynamic response or vibration response control of the structure. Unfortunately, we can not calculate damping, and I repeat my sentence: we cannot calculate the damping, we estimate the damping because it cannot be explicitly calculated. Therefore, we make certain assumptions. For example, one assumption that we make is damping is proportional to mass, or we say that damping is proportional to stiffness, for example. Now, when it is a structure which is in some fluid, we may consider that it is an external damping, and in that case, it is mass proportional damping. If it is an internal damping, for example, there is cracking in the reinforced concrete columns, or there is some friction at the joints in the steel columns. So in those cases, it is an internal damping which might be proportional, might be, not essentially, might be proportional to the stiffness. So that is the internal stiffness proportional damping. Obviously, in a structure, we have both of them present. So we typically say that it is mass and stiffness proportional damping. So that kind of damping is called Rayleigh damping, or it is also called classical damping. Now, this is again known, and this is approximation. This is not exact. This is with large assumption that it might be proportional to mass and stiffness. However, in this case, when we are trying to control the response by adding some external damping into it, naturally it will no more remain proportional to mass or stiffness, because we have added some artificial damping externally to the structure, and therefore it becomes non-proportional damping. And that non-proportional damping also cannot be called as classical damping. The structure becomes non-classically damped. If we do not add that external damping, then it is called classical damping. This is something which is classically known, that or it is assumed classically that the damping in the structure is proportional to mass and stiffness, and until we add the external damping. So this is something that we should know from the structural dynamics. However, when in addition to that external damping, there is some damping coming either from the soil structure interaction part, or if you have combinations of the structure. For example, you have a bottom floors reinforced concrete, and after that one has added new floors, but those new floors added are made out of steel, so it is a hybrid structure. You have combinations of two different kinds of structures, and thereby the mass and stiffness proportional damping, though it is present there, it is still in the category of non-classical damping, because the damping levels are different. Whereas reinforced concrete gives a damping level of about 4 to 5% depending on how much cracking has been induced, the steel structures can give up to about 2% of the damping. So there is a difference in the damping in the structure. Now that has effect directly on the frequencies or the modal values, or the mode shapes of the structure, which are the natural properties, because these are dependent on the mass and stiffness, and then from that we calculate the natural frequencies of the structure, modal frequencies, by solving the eigenvalue problems. And in that, we after that calculate the damped natural frequencies, and those damped natural frequencies, depending on how large the damping is, they are affected, means they are shifted because of presence of the damping. Now, based on the classical theories of modal superposition, if we have linear structures mainly, in that case, we can easily use the superposition of the modal response quantities. However, if there is extreme non-linearity present in the structure, we may not be able to use the modal superposition technique. They are typically for highly nonlinear systems or structures or dynamical systems. We tend to use the time history analysis. However, when we are carrying out the model superposition, again we need to rely on the statistical approaches in order to evaluate the total response. Now, those statistical approaches are something that you guys are already familiar with. You might have studied that in your structural dynamics, and those statistical approaches are square root of sum of squares and complete quadratic combination, means SRSS and CQC rules, depending on how closely or how widely these frequencies are separated. Again, if it is a long structure or tall structure, the classical theories of structural dynamics based on the lumped mass approach may not be directly applicable, and we may have to tweak in the equations of motion. So to summarize this, there are different kinds of approaches available for developing the governing differential equations and solving them for response evaluation of the structures, and those are categorized into lumped mass systems and distributed mass systems or continuum systems. In most cases, we follow still the lumped mass system. However, for some important structures, we may go with the continuum or finite element approaches, and especially when we have the soil structure interaction kinds of problems, or we have liquid structure interaction kinds of problems, then the lumped mass approach becomes more approximate. There, the continuum approach or finite element based approaches are more suitable. In case of lumped mass approach, typically we lump the, in case of buildings, the mass is lumped at the floor level, and the masses of the columns is added to the floors so that they only provide the stiffness, and their mass is considered here lumped at the floor level. And even for this kind of a three-dimensional oriented building, means where the members are in all three directions of the structure, they can be modeled at each joint or each node, and thereby the inertial forces are developed at the nodes and the stiffness forces are developed within the members, either vertical members, means lateral load resisting elements, or in the beams. Now, in today's presentation, our focus is on the earthquake ground motion, and to some extent on the wind loading, because both of them, they impose lateral loads on the structures. The wind loads, they apply lateral load, whereas there are lateral forces induced in the structure because of the inertia property of the structure. So let us focus on that and then see as to how to control those responses in the structure. So for this kind of a system, we develop the equation of motion for multi-degree of freedom system under either base excitation or the mass excitation. When I say base excitation, it is from the seismic case, and when I say the mass excitation, it is from the wind case. Please note that in both these cases of dynamic excitation, the governing differential equation remains almost exactly same. The reason why I'm saying almost exactly same is here. You can see that in case of seismic excitation, this is the inertial excitation, and whereas in case of wind loading, it is a direct load which is applied at the nodes, if it is a lumped mass system. Now, this equation, I'm sure most of you are familiar with this. When we write the equilibrium equation for the entire structure, the right hand side is 0 in case of earthquake, because here we are talking about the absolute acceleration. That absolute acceleration consists of two parts: the relative part of the acceleration and the ground acceleration. When we split this into two, there are two mass times acceleration components, and one of them related to the ground acceleration. If we take that on the right hand side, it gives the negative sign, and then we rewrite that equation in this form. The reason why I have specifically given these details, particularly for earthquake excitation, is please note that earthquake is not a load. I repeat, earthquake is not a load. It is inducing some seismic forces in the members, but actually there is no load applied on the structure. Whereas in case of wind, it is a load applied on the structure straight away. So therefore, in case of base excited systems, there is some kind of a pseudo or fictitious or imaginary load acting on the structure. There is actually no load acting. This becomes important to control the response of the structure. Now, once we write this governing differential equation, what do we do ahead? Ahead of that, our objective is to calculate the displacements at each node, the velocities, and the acceleration quantity. So these are the unknowns. Unknown displacement, their time derivative of displacement is velocity, and then second time derivative of displacement is the acceleration, or first derivative of velocity is the acceleration. We need to calculate these three unknowns. So what is known? Mass and stiffness explicitly known. C, we make some assumptions and calculate it. Mass is known. External excitation, we have to take that as a known quantity. Some earthquake excitation time history we take into account in order to solve this equation. So unknowns are x dot and x double dot. Knowns are mass, damping, stiffness matrices, and the external excitation. Once we solve this, once we see that there are some displacement, velocity, and acceleration, our objective is to reduce them down, to bring them down, to mitigate these response quantities. We need to reduce down the displacement so that the drift can be reduced and the serviceability can be made if it at all required. We also reduce down the velocity so that the kinetic energy part can be reduced down, and most important, we need to reduce down the acceleration. The reason why we need to reduce down the acceleration is the forces induced in the structure are proportional to the acceleration. So mass times acceleration is the inertial force, and that inertial force is basically the seismic force induced in the lateral load resisting elements. I'm using this term lateral load resisting elements instead of saying columns. Is there are other lateral load resisting elements which are important in the design of earthquake, uh, earthquake resistant members, because there are some shear walls, for example. So shear walls are also lateral load resisting elements, and the forces in the shear wall can also be calculated once we solve this differential equation. When we talk about the structural response control or vibration control or dynamic response control, our objective is to control the response, which is displacement, control the velocity response, and control the acceleration response. Now one may argue that okay, during the earthquake, because it is once in a while event, I don't care about the serviceability. It maybe in terms of displacement, let large displacement happen. Velocity, again, I don't care if it shakes a lot during the earthquake, because earthquake will last for a few seconds or maybe for a few minutes, so it's okay. But what is important is the acceleration, because that acceleration times mass is the seismic force in the structure, and thereby my focus might be on controlling the seismic forces. So as a designer, we take a conscious decision as to what are we going to control, either only displacement or velocity or acceleration or displacement acceleration. And that is the essence of structural response control. Which kind of device are we going to use, and by using that device, which response control are we going to achieve? It could be displacement control, it could be velocity control, or it could be acceleration control. Accordingly, when we add certain external element into this, either we change these mass, damping or stiffness matrices, or we add some external damping force in the structure. So that is what we are going to see. Uh, are there any quick questions? Okay. Now, for long structures, typically those structures such as bridges, there might be different kinds of excitation experience at different piers, means at different pier location, because the length is larger. There could be 100-meter or 200-meter long bridge, and thereby we cannot take, I'm just going one slide back, we cannot take the same earthquake excitation received at each of the pier location. So there, in that case, we may change the excitation depending on how the ground is and how the attenuation is happening. So in that case, we have to change our equilibrium equation in a sense that we have different kinds of excitation at received at different input points to the structure, different supports to the structure, such as the long bridges or even long plan buildings, and that is called multi-support excitation. Now, from this, if we take out the terms of the external excitation and damping, what we are left with the natural properties or inherent properties of the structure, such as mass and stiffness. They are independent of the external excitation. Now, if we express it in the form of an eigenvalue problem and we solve it, what essentially we calculate are the modal frequencies and mode shapes. Now, why that are important to us? Whenever we are intending to use some response control device, we may actually see what is its effect on the modal frequencies and mode shape of the structure. Be it base isolation, be it any kind of damper such as viscal damper, viscoelastic damper, or friction damper, they essentially influence the natural properties of the structure. Particularly, for example, in case of base isolation, there is change in the mode shape. We have one additional mode shape corresponding to the isolation mode, which is orthogonal to rest of the modes, and thereby we reduce down the response of the structure. Or when we add, let us say, a tune mass damper on the structure, there is change in the modal frequencies and the fundamental mode. If we are controlling the first modal response, then we split into two modes and we have a different modal quantities corresponding to the first and second mode. So that we will see in the subsequent slide. So mostly I have talked about the base and mass excitation and how we calculate these different uh, quantities such as mass, damping, stiffness, and then our objective is to control the dynamic response or vibration response of the structure. So most of these things I have already talked about. This only summarizes the structural dynamic concepts. Now, there are two parts again, the mass excitation and base excitation. In case of mass excitation, we calculate what is the load acting at different nodes if it is a lump mass modeling approach by multiplying the pressure applied by the wind on an exposed surface and then calculate the force acting at that level. Typically, it has this kind of a profile because of the friction with ground and trees that are there beneath. But otherwise, we get almost the maximum velocities here, which are free velocities, and thereby we get a uniform high pressures at the top. So this is especially important for the tall structures. For low-rise structures, though, they are more prone to earthquake rather than wind, which is the focus of the today's presentation. So in case of earthquakes, there are different kinds of earthquake ground motions depending on what site we are talking about. If it is a rocky site, we may have higher amplitude and large frequency component kinds of earthquake. If it is a soil or soft soil, then we may have a long period or low period, depending on again how the soil amplification is taking place. If there is a reclaimed land, such as let's say in Mumbai, we may have a very fine excitation, something similar to the Mexico City earthquake, for example. So all these characteristics of the accelerogram of earthquake ground motion, they have direct effect on how the structure would respond. And typically we quantify it in three terms. One, the maximum acceleration in an earthquake first. Second, what is the frequency content? For example, here the frequency content is lower as compared to this. There are a lot of high frequency components involved in this excitation. And the third and the last one is the duration. Now, these days duration is also becoming important. Earlier, it was not per se a design parameter, but now there are certain areas where long duration earthquakes are becoming more and more prominent. For example, in Japan, they are expecting an earthquake which may even last for 15 to 20 minutes or even maybe 30 minutes, half an hour. So that becomes quite important because there is a lot of to and fro motion happening. Though there is, I always say that earthquakes are not fatigue loads. Earthquakes are not similar to fatigue load because in case of fatigue, you need to have large number of positive negative or positive positive or negative negative cycles of loading on the structure. In case of earthquake, you do not have those many cycles or repeated cycles of loading. However, if it is a long duration earthquake, it is kind of comparable with the fatigue loading as well. But let us right now talk about the short duration earthquake so far, and sometimes later we will talk about the long duration earthquake. So if we have a look at our Indian standard codes, and for that matter even worldwide also, most of them they do not much worry about the long duration earthquake. However, indirectly these codes and standards they deal with the frequency content. I am saying indirectly, but they directly deal with the earthquake intensity measured in terms of the peak ground acceleration. So the intensity parameter that we essentially take into account in the structural design is the peak ground acceleration. So whenever we have some time history, we focus on the peak ground acceleration and then start designing our structure as well as the response control devices based on how the structure is responding to a given intensity of an earthquake. Originally, without any external device, we may get the force deformation behavior, something as it is seen here in the figure B, where the area enclosed within the hysteresis loop is very less relatively. So if we see on the force deformation loop here closely, there is kind of a sudden failure in the structure, and this is a non-ductile behavior which is not recommended for the better performance of the structure in seismic prone areas. We need to have a larger area enclosed so that there is large either dissipation of the energy or absorption of the energy. I will come to that distinction between energy absorption in the structure and energy dissipation in the structure in a little while. However, what we prefer is this kind of a bulky, fat, or larger area enclosing kind of a loop for force deformation. Thereby, there is more seismic energy dissipated here, and then rest of the structure could be safeguarded. So typically, this goes into the capacity-based design or capacity design of the structure, again, which I will touch upon in a little while. If we use some friction element in the structure, or if we use some special devices in the structure for the energy dissipation, then the hysteresis models look something like this. For example, it is elastic, perfectly plastic, because this line is horizontal and this is a linear part, and there is a yielding at this level. So it is elastic and perfectly plastic. So there could be some devices which are elastic, perfectly plastic, or there could be some devices which are elastic, which is similar to this, but this there is some slope here, it's not exactly horizontal. So it is called plastic, but this is not perfectly plastic, there is some hysteresis here. So elastic and plastic with hysteresis. And where there are some stick slip models when it is based on friction. So there is stick mode, then there is slip mode, again there is stick mode, so on and so forth. So essentially these are friction based model, and again we make an assumption that it is a Coulomb friction that we use in modeling these things. Of course, some if somebody is interested in having some lubrication in the friction elements, then one can use the Steinbeck effect and take into account that um, wet friction. Otherwise, we always use the dry friction based on the Coulomb's approach. Now, how do we incorporate these devices in the structure? So, first of all, I'm showing some of the failures, and then we learn from them and how we protect the structures thereby by adding some external devices. What you see here is a bracing system which is conventionally put. This picture is from the seismic prone cities in Japan. What you see here is those bracings have yielded, and because of that, there are some local damage, but the overall structure is still intact. Same here, you can see that there is some yielding in the bracings, and whenever you see yielding, they are absorbing energy, not dissipating. So whenever there is metal which is yielding, it absorbs the energy, and we do want that. It is intended. But unfortunately, in India, the use of these kind of devices, or even for that matter, the simple bracing systems, is not so widely adopted. And in most cases, in the rural parts, we have non-engineered structures. They are built by masons or those who are not trained in the constructions, and thereby during the earthquake they experience these kind of catastrophic failures, causing a lot of death toll. Even some so-called engineered structures, they also experience collapse because though they are engineered structures, the best practices of earthquake resistant design have not been followed in their design and construction. Whereas if we see the structures in the seismically advanced countries such as Japan, or in US, the West Coast, the California region, they have adopted the best practices in earthquake resistant design, and thereby by constructing those structures earthquake resistant, they are able to save both the human lives as well as the loss of property and loss of business. The way it is done is either by using some conventional approaches of earthquake resistant design, or by using some of the advanced devices, which is again we are going to focus today. So how do we control the response of the structure? We do that either by increasing the flexibility of the structure in case of seismic case, so that if you see on the response spectrum, we are going towards the part where the spectral ordinates are diminishing or they are lowering down. Uh, in addition to that, for the ambient cases and for those earthquakes which are not so intense, means their PGA is lesser, we may also look into the serviceability conditions, whether serviceability is met or not. In addition to that, we have some predictive models wherein we check as to what is the possible earthquake excitation at different time steps, and for that we we design these response control devices that they are not only helping during the extreme earthquake case, but they are also helping in the ambient conditions as well. There is a lot of uncertainty involved in this, and that uncertainty these days we do take into account. A detailed discussion on that again we will have sometimes later. So focusing on particularly the fundamentals of the vibration control and how we use them in our buildings and structures. Typically, we incorporate some device in the structure in the form of either a bearing or in the form of some dampers like shock absorbers that we see in the automotive, let's say in the cars or in the bikes. Or we put some tune mass dampers on the structure, and all these passive devices having no external inputs as such as the base isolation or the dampers or the tune mass devices, they can be converted or they can be put in the semi-active mode or in the active mode as well. Again, I will talk about that in a little while. These devices may function for both the purposes or separately, ambient vibration conditions or the extreme vibration conditions, either because of the earthquake or because of the wind. Now, we these days worry about the performance of the structure during the different levels of earthquakes, and that falls in the category of performance-based earthquake design. So, even in the structural response control as well, we are in a position to look into what are the different damage states and what is the performance level threshold that we are achieving by incorporating these devices in the structure. Typically, for the lifeline structures such as the hospital buildings, we always anticipate that it should have operational level of performance. It means during and after the earthquake, the hospital should remain functional without requiring any maintenance or rehabilitation as such. So even for hospital buildings, we in a way do not prefer the immediate occupancy as well, because what immediate occupancy means that during the event ongoing activity on excitation, the occupants of the building are evacuating, they are going out. However, after the event is over, they are again coming back and start using the structure without requiring any rehabilitation. However, just imagine for an hospital building, the patients where the patients are residing, depending on their health condition, they may not even able to go out of the building, right? So they may even just remain there. It will take a lot of time for them to evacuate the building, and by then the earthquake might be even over. So for the hospital buildings in particular, it is recommended that we have the operational level of performance. It means there is negligible damage, the damage which doesn't require any attention immediately, which can be taken care later. Now, the classical, old theories of articulation design may not be able to give that performance level of operation for a considered or for the design earthquake. So thereby, we need to rely on some control devices, say for example, base isolation. Is there any quick question on this? No. But for the other kinds of structures, we may also decide what is the performance level we want and how much damage we can allow in the structure. So to do that, to control the response of the structure, we have these different options available. There are mainly two categories of the controls. One is the passive control, another is the active control. Semi-active control is actually part of the active control only, or we can modify the passive devices to convert them into semi-active devices by having some tweaking in them. Again, the fourth one, the hybrid control, it is not a separate control device or category as such. If we have combinations of different devices, it simply becomes a hybrid category. Now, how these passive devices and active devices are different from one another. So, in the passive devices, there is no requirement of external power source. They function, they work based on their own properties, such as they have some stiffness, they have some damping. That stiffness damping remains the way it is during the excitation, and we do not change or we do not tweak it during the excitation. Whereas in the active control devices, there is some external power input to the structure to that device, such that that device will have its own property changed during the excitation itself, as per the needs, as per the demand. For example, there is change in the stiffness. For example, there is change in the damping. So those are the active devices. So there is a clear difference between passive and active devices. Passive device function of their own with their own properties, whatever they have. Whereas in the active control, we are in a position to change their properties, their dynamic properties, specifically during the excitation or during the loading. Now, how these active devices are different from the semi-active devices? So in case of active devices, the power requirement, the external input requirement is very high. Now, typically in the structural engineering, we have massive structures, and for controlling the response of that massive structures, the external input of the power is very high. When I say power, it could be just electricity, the electric power, just to operate the pumps for hydraulic to generate the hydraulic pressure or the actuators. That requirement in case of civil engineering massive structures is very high as compared to lightweight structures such as cars, automotives, in the automotive industries or even in the aerospace industries. Let's say for the wings, if you are controlling the response of the wings, you need a small power because it's not massive. So active control is very popular in the automotive or mechanical and aerospace industry. The civil structures, because they are massive, it's not so popular. In civil industry, rather than active control devices, semi-active devices are rather suitable because the power requirement in case of semi-active devices is very low. How much low? It could be as low as even use of batteries, simple batteries. Now, even in case the batteries are not functioning, they have discharged, they have not been replaced or maintained, these semi-active devices can also function as passive devices. It means whatever their properties are, no matter if they are changing during the excitation or not, they can still be effective in controlling the response of the structure. And that is the reason why semi-active devices are very, very popular these days. Though their use, especially in Indian context, are very low, still people follow the conventional passive control devices. However, there is increased awareness on use of the semi-active devices. So depending on whether the external power is required or not, external energy input is required or not, we categorize into passive and active devices, and depending on whether it is a very high voltage required or very low voltage required, we categorize into active and semi-active. And if we have combinations of the devices put in, then it is the hybrid control device. Okay, I have already covered this part, so I will go ahead. So there are different kinds of vibration control devices available, such as base isolation. Again, there is some different schools of thought, particularly in Japan. They do not consider base isolation as a vibration control device, but in my opinion, base isolation is also a vibration control device. However, there is no different schools of thought insofar as the viscoelastic dampers or tune mul dampers or multiple tune mul dampers are concerned. They are all vibration control devices. If we have their inherent properties used in the vibration response control, then they fall in the category of passive control. If we have their property changed during the excitation as per the requirements, then they are called active or semi-active control devices, depending on what is the power input required. In this In this case, what you see is a building which is having some devices put in, and when you see this kind of arrow, it means it is a variable stiffness. For example, this is an indicative diagram that there is a possibility that you can have the variable stiffness, you can have variable damping, which is varying during the excitation as per the requirement. And typically when you have the large energy dissipation, essentially you are talking about the non-linearity in the structure. More the non-linearity, more the area under the force deformation loop, bulkier is the force deformation loop, hysteresis loop, more is the energy dissipation and more protection that we can obtain. Now, that kind of nonlinearity or that kind of higher damping can be introduced in the structure by large number of ways, and it will become a very exhaustive long list as to what are those different approaches that we can incorporate these nonlinearities. However, still some salient names have been taken here, such as the tune mass dampers or liquid column dampers, MR dampers, which are magnetorheological dampers, or electrorheological or ER dampers, then active mass dampers, smart dampers, so on and so forth. There are a large number of such devices available. And even within the active and semi-active control, depending on what is the control algorithm, what kind of code has been used in order to control and change the dynamic properties of the damper, such as the feedback control, forward control, linear quadratic or linear quadratic Gaussian, depending on the probabilistic response evaluation. The control algorithm changes, and the achieved response reduction also changes. There are different ways in categorizing these vibration control devices, but some main categories are, as I have said earlier, the passive, the active, semi-active, then hybrid control devices, and then within that again, if we take one of them, let's say the base isolation, again it could be based on a rolling isolation system, sliding isolation system, or the elastomeric system. Again, within those there are subcategories, so on and so forth. So there are large number of options available. The takeaway message from this slide is the designer for application design of the structures has several choices to pick from, whichever device, either based on the control requirement, whether it is displacement control, velocity control, acceleration control, or combination of them depending on the availability of those kind of devices in that particular location. For example, in India, some of these devices are available, some others are not available, so on and so forth. Once we choose one particular damper out of these different possibilities, we can design our structure accordingly and see as to how it responds. While choosing that devices, essentially what we are adjusting or what we are in a way manipulating is either the mass of the structure, or damping of the structure, or stiffness of the structure, or even we are not allowing the external excitation force to enter in the structure like in base isolation, or we apply certain external control force. So essentially, from the structural dynamics viewpoint, which I have talked in the beginning of this class, we are playing with the mass matrix, we are playing with the damping matrix, we are playing with the stiffness matrix, we are playing with the excitation force on the right hand side of that covering differential equation. So overall, what we have in our hand to control the response of the structure is that simple equation. You have three terms: the inertial force term, the damping force term, the elastic or restoring force term, and the external excitation. You can play only with this, and typically it is better to play with the damping. So damping device, therefore in some cases we call these are damping devices. Essentially we do not much worry about the mass because mass of the structure remains the way it is, and the seismic forces are proportional to the mass. So typically, in order to reduce down the seismic forces on the structure, we tend to have lighter mass structures as much as possible, but it goes into the material, what kind of materials we are using in the structure. So in case of vibration control, the focus is not much on how we are building the structure made out of either reinforced concrete or steel, and they are massive structures. So controlling the mass is something which is challenging in case of earthquake excitation. But increasing the damping capacity and changing stiffness to some extent, these are really possible. Avoiding the external excitation to reach to the structure is again rather challenging in a way, And applying the external force is also very challenging for tall and massive civil engineering structures. So focus still remains on change in the damping and change in the stiffness. So our objective is to change the damping and stiffness of the structure. So what are the options available? Very quickly, this schematic shows different options available. For example, we have base isolation, where we isolate the whole structure from the moving ground or the moving foundation by using these kind of isolators. So rest of the discussion I will reserve for tomorrow's class. The other option is tune mass damper. We can install the tune mass damper at appropriate location. The most favorable location is at the top of the structure, which experiences the large displacements. If that tune mass damper is fitted with some active or semi-active device, then their properties can be changed during the excitation stage itself, so that we achieve larger response reduction or larger dynamic response control or vibration response control. Or we can have some bracing systems or some active tendon systems. This AT stands for active tendon. Now, something that fascinates me is this kind of a system. Of course, there are two combinations shown here. If you are using them together, then it becomes a hybrid system, but not typically we use two systems together. Either we use the active tune mass dampers or we use the active tendons, but it is only for the illustration purpose. I would like you to focus on how the active control system works in general in a very simplistic manner. So typically in the active or semi-active response control, we have some sensors placed. Those sensors could be either on the ground or at the foundation level to measure the earthquake ground excitation received to that structure. That is the input to the structure. So those can be simple accelerograms which measure the acceleration, and they will measure the ground acceleration xg double dot quantity. In addition to that, there could be some other sensing devices which are sensing the floor response, either floor accelerations, for example, or velocities or whatever. So they typically measure the floor response. So you can see, for example, there are accelerometers installed at the floor level, and their measured quantities are fed to a computer. So you can see the arrow here. The arrow is going towards the computer. So ground acceleration is measured by the accelegrams and it is fed to the computer. So the computer has received as an input data of external excitation as well as response of the structure, right? The flow response of the structure. So that is the input. Based on that, we do some coding. We write some program as to if this is the excitation, if these are the flow responses for a given structure, what should be the control force? So we calculate that in real time when the actual earthquake is happening. And then we give a feedback control to our devices that this is how your dynamic property should be. We dictate that through that code, that this is how the stiffness should be, this is how the damping should be. Changing the mass during real time is rather challenging. So because of that change in the stiffness and damping, we can further reduce down the response of these floors in the subsequent time steps. So we give that feedback signal, or we give that control signal, or we control the response of the structure by changing the properties of that control device, and therefore it is called active or semi-active control. Similarly, as you can see here for the active tune mass damper, we send the signal to the active tendon system, and then we dictate how the tendon should behave, which one should be taut, which one should be slack. So for example, there is an actuator here, and we give that signal to the actuator. For example, if this building is moving on the right hand side of the observer, then we would like to pull this tendon such that we are pulling it back, or we are not allowing it to further displace on the right hand side. It means this actuator will go from our right to left, because when it is moving in this direction, it will pull this tendon, and because it will pull that tendon, the structure will not be allowed to go in the right hand side. Similarly, because earthquake is to and fro motion, when because of the inertia it is thrown on the other side, We would like to pull this diagonal tendon, and for that matter the actuator has to have its ram moved from our left to right. So depending on how this flow is moving in real time, by measuring the response of that flow through this sensor, the computer gives a signal to the actuator in which direction it should move. Please note that there is some time lag involved in this, because this response has to be measured, fed to the computer, the algorithm runs, means the code is executed, then the signal goes here, which is analog signal, digital signal, that is again controlling the actuator here, and then actuator is actually applying the mechanical load on the structure. So obviously there is a lag, and most of the research focuses on how to reduce that lag by having some predictive, means what is happening in the next time step. Predictive laws are being developed. Again, before I go any further, have I been able to explain how this semi-active or active response control works? Because the rest of my discussion, active control, will mainly revolve around this. Any questions so far? No quick questions? Okay, I'm glad that I'm able to explain this with a lot of clarity. Thank you. Okay, so these are some schematics showing how the passive bracing systems and base isolation and tune mass dampers are represented, and how do they function, that we will see subsequently. So for any civil infrastructure, we can put the energy dissipating devices, either passive, semi-active or active, in the form of dampers internally or in the form of base isolation systems, to separate that structure from the oscillating ground, or installing some tune mass dampers on top of that. So out of this, I will first talk about the tune mass dampers, then I will talk about the other dampers, and tomorrow I will talk about the base isolation. So tune mass dampers are very classical device based on the fundamental principle of structural dynamics, which is resonance. So the parent structure could be a multi-story building, could be a bridge, when the bridge is subjected to either earthquake excitation or even the live load. When the vehicles are moving, the bridge starts oscillating. So that entire structure can be represented as a multi-degree of freedom system, or that multi-degree of freedom system can be converted into an equivalent single degree of freedom system. So this MCK means this mass, damping and stiffness is representative of that one equivalent single degree of freedom system of the parent structure, the main structure, the response of which is supposed to be controlled, means displacements to be reduced, acceleration to be reduced, velocities to be reduced. Typically, in case of flexible structures, displacements are something that we need to control or reduce. So for that purpose, we essentially go with the displacement control devices, not much paying attention towards the force control devices. Tune mass damper is one such device which is typically used for displacement control. In tune mass damper, we have certain mass installed on the top of the structure, and it is connected to the structure by some stiffness and some damping. So that stiffness and damping and mass corresponds to the tune mass damper. Now the word tune comes from what is the frequency of this device and what is the frequency which we are controlling. Typically, the larger mass participation is in the first few frequencies, especially the fundamental or the lowest frequency. So there we have the largest mass participation, and thereby the final response is governed mainly by the first mode. So if we are controlling the response of the structure in the first mode, we take the first modal frequency and we tune that frequency here by adjusting the mass of the tune mass damper and stiffness of the tune mass damper. So tune mass dampers can be designed by adjusting the mass, or by adjusting the stiffness, or by adjusting both of them. There are three ways of designing the tune mass damper. And when we talk about the matching of the frequencies between the two, we match their damped frequencies, not undamped frequencies, because damping is inherently there always. So we calculate the damped first mode frequency of the parent structure, we calculate the damped natural frequency of the tune mass dampers, and when they are matched, in that condition only we get the maximum dynamic response reduction of the structure. Why do we get so? So that we will see in this animation. We are seeing here the response of the main structure without installation of the tune mass damper. So again, this is a representative structural dynamic picture where you have a single degree of freedom system. There is some excitation here in this direction. Again, it doesn't matter which direction it is as of now for our discussion. This is the larger uppercase mass, and this is the uppercase X, which is the displacement of this. There is some stiffness element here, and there is some dashpot or damping here. Under this excitation, the amplitude in whatever unit is somewhere around 3 units. Now, when we install a tune mass damper, a small mass to that, the black colored response of the main structure is barely visible also because it has reduced down very drastically. There is a black color curve here of uppercase X, capital X. Whereas the lowercase x, which is the displacement of the mass, as you can see here, the mass is oscillating quite vigorously and it has large amplitude, even more than 3, which was for the main structure before it was controlled. After control, the main structure is receiving very less of excitation, and the more energy is being dissipated by that smaller auxiliary mass installed on the structure. Now, why does that happen? It typically happens because when this mass is moving in one direction, let us say it is moving in the upward direction, because of the inertia of the small mass, it tends to move in the downward direction. Right? So it means it resists the movement of this main mass going upwards. In the next time instant, when this mass is going down, because of the inertia, the small mass relative to that will come closer to it. It means it is moving in the upward direction and it is applying a force in the opposite direction of the motion of the main mass. Now, because of the tuning, because their frequencies have matched, they will always be working against each other, and there will be a phase difference of 180 degrees. It means if this main mass is going down, the auxiliary mass, tune mass damper, will go up. If this is going up, means main mass is going up, this will go down. And it will keep on happening because their frequencies are same. Had their frequencies been different, then there might be a possibility at one particular time instant, this mass is going down, the main mass, and even this auxiliary mass is also going down. It means it is further pulling the structure. It means there is an amplification in the response, which we don't want, and that is called detuning of the tune mass damper. We don't allow that. We don't let that happen. Even in the real life construction, if time permits, I will talk about that as to how we control the response by having a perfect tuning, perfect frequency matching, so that there is a resonance. Please note that when there is a resonance, we typically say that the structural response amplifies, and it is not advisable to have resonance in dynamical system to control the response. Here we are actually using the resonance to control the response of the structures. So this is one of the most attractive passive vibration control devices used to reduce down the vibrations of the structure based on the principle of structural dynamics resonance concept in a way. So that was from the structural dynamic perspective. But in real life, how do we have them installed on the buildings, particularly the tall buildings, which experiences a lot of lateral oscillations, either because of the earthquake or because of the wind? One may argue that typically the tall buildings are not much sensitive to, or their design is not governed by earthquake. Their designs are mainly governed by the wind. Yes, it is understood, but right now that's not the point of discussion. The point of discussion here is, no matter whether it is a low-rise building, mid-rise building, or tall building, how these different control devices help in mitigating or abating the vibration response. So in case of tall buildings, the most preferred location of installation of the tune mass damper is the topmost floor, which experiences the largest vibration amplitude. Now, in the subsequent slide, what you will see is that when there is some excitation, either in the form of base excitation or wind excitation, the uncontrolled building, the building which has not been fitted with the damper, experiences a lot of uh, um, large vibration amplitudes, whereas this building response, the vibration response is reduced and the tune mass dampers works. However, it takes some time for activation of the tune mass dampers because the earthquake excitation in particular takes some time to reach up to the top of the structure. So if you compare both of them, you will understand that initially for few seconds, both the buildings behave more or less similar in a similar manner. But after those few seconds are over, when the tumor damper gets activated, then the response of this building, which is controlled, reduces down quite drastically as compared to the uncontrolled building. So you can see both the buildings are oscillating, but now these buildings oscillations have reduced and mainly the tune mass damper is oscillating. Of course, this is again rewinding. So after rewinding, you can see that from the beginning they experience similar kind of excitation and later on this keeps on oscillating, but this building oscillation reduces down when the tune mass damper is used. So quickly seeing how the damping is enhanced. So this is not the material damping. This damping is a different kind of damping introduced to the structure and it is quantified in terms of effective damping. So when we have the exact matching of the frequencies, we get high damping, high effective damping. And if there is no matching of the frequencies, it means if detuning happens, then the damping reduces down and there is even a possibility that it goes into negative. It means the instead of reducing down the amplitude, there is increasing the amplitude. But anyway, that's not again the point of discussion. Also, if we have the larger mass put on the top of the structure as a tune mass damper, it gives a better effectiveness in terms of increase in the damping. However, there is limitation. Just imagine a huge mass is to be put on the top of the structure. You have to carry that huge mass at the top of the structure, which is very difficult. There are some practical limitations, but if you have the higher mass of the tune is comparatively higher than the modal mass of the structure, then we get the higher response reduction, higher damping, higher effective damping in the structure. And typically for perfectly tuned structure, you get the response reduction better. But please note that the peak is not at 1, it is slightly lower than 1. I will leave this as an open question if somebody would like to know the reason behind that. These kind of tune mass dampers have been installed in different kinds of structures across the world. Typically, as I have said, they are more popular for the tall structure, relatively tall structures such as air traffic control towers. Even in Delhi, also at the airport, we have a air traffic control, the response of which is being controlled by a tune mass damper. Similarly, some tall buildings like the Hancock Tower in Boston, or there are Sydney Tower, City Center, they are all controlled by the tune mass damper. So that is one kind of damper. Another kind of damping device is used for dynamic or vibration response control of the structures are the viscous dampers, viscoelastic dampers, friction dampers, yielding dampers, and so on and so forth. There are large number of categories. I have taken only some for the example purposes. Again, within them, if I say viscous damper, within them there are different categories of viscous dampers. In viscoelastic damper, there are different categories of or types of viscoelastic dampers or friction dampers or yielding dampers, as many as we may not be able to cover them in today's discussion. But I'll give you a general philosophy or how do they function or work and help in vibration response reduction. So essentially they increase the damping in the structure, and as I have said earlier, because now they have been externally added, it is not obviously proportional to the mass and stiffness, so they convert the structure into a non-proportional or non-classically damped structure. And most of the energy is dissipated, which is that area under the force deformation curve, through some mechanism, and that mechanism depends what kind of damper we are using. If it is a fluid damper, then in the fluid viscosity the energy is dissipated. If it is viscoelastic damper, that viscoelastic material that we are using in these devices, there is energy dissipation. If it is friction damper, then energy dissipation happens in the friction between the two sliding surfaces against each other. In these three devices, viscous dampers, viscoelastic dampers, friction dampers, we say that energy is dissipated. Whereas if there is metal yielding, which most of the structural engineers are familiar, when we apply certain load uh, to certain extent, excuse me, it behaves linearly elastic, where the Hooke's law is obeyed, and after that there is a yielding, and the non-linearity begins. And when there is this non-linear curve, force deformation curve, the area under that is the energy absorbed, not dissipated. So yielding devices or yielding dampers, they are energy absorbing devices where there is some yielding of some kind of metal. Typically steel is used, but even in addition to steel, aluminum is also a very good yielding material having large ductility. But again, there are a limited number of structures where the aluminum based yielding damping devices have been used. So those devices are essentially the energy absorbing devices. Let's quickly see how they internally look like. First of all, the viscous damper. It is exactly same as what we see in our day-to-day automotive vehicles, such as the cars or bikes, where you have the shock absorber, or sometimes it is also called shock ups. So it has a cylinder. Within that cylinder, there is a piston. That piston divides the cylinder into two chambers, two compartments, and there is a viscous fluid into this. Typically, silicone is used, and there is a relative displacement between the two. If there is no relative displacement, the piston is at a static position. But when the oscillations takes place, this piston starts moving inside this chamber, and there are typically some orifices here, and the compressible silicon fluid moves from one compartment to the other, and in that process, because of the viscosity in the fluid, there is a energy dissipation, large amount of energy dissipation. You can see that there is no change in the stiffness of the structure. It means the modal frequencies will remain the same, the natural mode shape, natural modal frequencies. However, damped natural frequencies will change because now there is a huge amount of damping added. How huge? So typically, as I have said, in case of steel structures, it is about 2% damping. For concrete structure, it is 4 to 5% damping. Whereas these viscous dampers can give you a damping of even 10%, 15%, or even as high as 20%. It depends on how these damping devices have been designed. Now, for example, there are orifices here. Orifice means simple hole, right, in the piston. So when the piston is moving from our left to right, the fluid here is moving from this chamber 2 to chamber 1, post in the opposite direction. But imagine that by some means you are in a position to change the diameter of the hole. Okay? Then what's going to happen? In that case, the movement of that fluid from chamber 2 to chamber 1 and vice versa, when the piston is moving on the left hand side, the fluid will move from chamber 1 to chamber 2. By changing the diameter in real time, we can control the flow of fluid from one chamber to the other, and the same viscous damper can then be termed as either active viscous damper or semi-active viscous damper, depending on how much external energy or electric energy or voltage that you require to change the diameter of the hole. I generally again leave it to the students to tell me how they should be in a position to change the diameter of the hole in real time. Again, I leave the second question to all of you. If somebody of you can answer that maybe towards the end of this class. The other devices are the viscoelastic damper, where we have certain viscoelastic material put between these two arms moving relative to each other. So when it is strained, it provides both stiffness as well as damping in the structure, and there is change in the stiffness matrix and the damping matrix. Typically, it again gives a higher damping, maybe not as high as in the viscous damper, but relatively higher damping. So in this case, all the properties, dynamic properties of the structures are changed, including the stiffness matrix and the damping matrix together. Apart from that, there are other several devices which is not possible to cover all in one 1 or 2 hours. But still, some of the popular devices are the buckling resisting or um, BRBs, buckling resisting braces. In this, there is a buckling element. Typically, it is steel, and when you apply some compressive force on that, there is a buckling in higher modes. And in that process, there is because it is a nonlinear or inelastic buckling, there is energy dissipation. The other kinds of devices are the friction systems. Again, they have been commercialized, patented, and commercialized in the North America by one of the person from Indian origin, Mr. Avtar Paul. So he has developed these kind of cross bracings where there is a friction element in here, and when there is a relative displacement between the different these four nodes here, there is a energy dissipation in the friction element. Now one can think of having fabricated these devices, friction devices, in very different manner. So there are very large number of friction based devices which dissipates the energy. For example, again from the University of Toronto, there is one device which has been patented, and that is the slotted type of friction damper, where there is an oblong hole here, and when this bracing moves to and fro, there is a relative motion between these two plates, and the friction between the two plates dissipates the energy. Uh, some of the challenges in these kind of friction dampers is the restoring. After the earthquake is over, there is a tendency that in whatever displaced position the damper is, it will remain there. So you may require some external effort to bring the structure back to its original position. So these are some of the limitations, and there are some efforts being made to put them in a hybrid mode so that there is some restoring devices added. So at IIT Delhi, we have developed some such systems where there is a restoration has been added to the friction dampers. So I talked about the viscous dampers, I talked about the viscoelastic dampers, I talked about the friction dampers. The next devices are based on the energy absorption, which I have said is one of the categories in which there is yielding of some material. That yielding of the material could be at some location which is the weakest location. So this kind of damper is called X-plate damper, or it is also called the added damping and stiffness device, where we deliberately reduce down the cross section, where it means we are creating a weaker zone. And obviously when we apply certain load on this plate, it has a tendency to fail at a location which is having the least area of cross section. So thereby there is yielding at this cross section, and there is a large amount of energy absorbed here. Now we design the thickness of this plate in such a manner that for the design basis earthquake, whatever is the earthquake force getting induced here, it should yield. So we are deliberately making it to fail so that when it fails during the failure process, it absorbs large amount of seismic input energy, and that energy does not go anywhere else, so that the other members do not receive that seismic energy and they do not fail. So we concentrate the failure location at one place to this device, and after the earthquake is excuse me, after the earthquake is over, this failed device in a way we can replace it. The reason why I'm saying it failed, because simply that it has yielded, and that yielding was deliberate. We wanted it to yield so that there is energy dissipation, because that input seismic energy has to be dissipated somewhere or absorbed somewhere, because the energy conservation principle remains the same. It is a universal law. So that energy has to be diverted somewhere. So that diversion takes place in case of these added damping or stiffness devices in the devices, which can be replaced if required after the earthquake is over. So these are very attractive devices in that sense, and we can achieve a higher level of energy dissipation in the structure. Now, please note here that we have added stiffness in this structure, we have added damping in this structure. So our stiffness and damping matrices have changed. Of course, the mass is very small, so we don't care about that. Because of this, you have been able to divert the seismic input energy to a particular device. Okay, it means the other members have not received high seismic forces. However, what would happen to the acceleration? What would happen to the displacement? We have not much looked into it. So when we talk about the vibration response control of the structure, if we are so careful about what is happening to the displacement, what is happening to the velocity, what is happening to acceleration, what is happening to the seismic forces, then we will find that not all the devices are helpful in controlling everything. Some devices, they are able to reduce the displacement, for example, but at the cost of maybe higher acceleration. For example, if we have more stiffness added to the structure, the displacement reduced down because there is higher stiffness. However, higher stiffness means the frequencies have increased. Higher frequencies typically have higher accelerations associated. Now, if we would like to have both the accelerations reduced and displacement reduced, that device which only improves the displacement response control is not useful, which adds only the stiffness. We need stiffness and damping together. The damping might be able to reduce down the acceleration, and the stiffness might be able to reduce down the displacement and drift in the structure. So that is where the design of these devices becomes very important as to what is your control objective. The control objective could be reduction in all of these dynamic quantities. So that is where the design of these passive response control devices becomes important. Apart from some of these devices, there are certain other control devices available, such as the tune liquid column damper, in which there is a U-shaped tube installed on a floor of the structure, typically the top floor, containing some liquid, and there is a diaphragm having an orifice, and when there is oscillation, when that floor experiences certain excitation, because of the inertia of that liquid inside, there is change in the liquid column from one side to the other. For example, when the floor is moving from our left to right, the fluid is forced in the opposite direction because of the inertia. There is rise in this level here, there is drop in this level, and in that process of movement of the liquid from one side to the other side, there is the dissipation of the energy. Excuse me. So those were mostly the passive control devices. Their stiffness and damping do not change in real time. They remain what they are. But I have given you one example earlier as to how we put the active control or semi-active control systems in our structures or in the dynamical systems. So same is shown schematically here. For example, we have this tune mass damper, and there are certain sensors put. As I said, the sensors could be measuring the ground excitation, it could be measuring the floor responses. We give that as an input to the control computer, and then control computer generates the control signal. It goes back to the device, and the properties of the device change in the real time. So in a semi-active or active control devices, sensors are essential. Those sensors give input to the code, and then that code generates the command signal, and that command signal is given to the controller, and that controller changes its mechanical properties during real time. I have also explained to you how the active tendon system works in a real life. When this mass is moving in from, let us say, left to right, we want to restrain that motion of the mass. So we would like to pull it back by using this tendon. In order to pull that tendon, this ram may move from left to right. So when it is from right to left, so it is pulling this tendon back in this direction, thereby the motion of mass is restricted. Now, if the mass is moving from our right to left, we need to pull this tendon here, and in order to pull that tendon, this actuator should move from our left to right. So the motion of the actuator is in our hand. We control that using that computer signal. Depending on which direction we would like to pull the mass, we keep on changing in real time. Excuse me. And that is called the active tendon system or AT system. Now, some quick discussion on the active systems and semi-active systems. So typically, we have borrowed some of these ideas from electrical engineering. So I have converted those terminologies into civil or structural engineering terms. So we have a dynamical system of which the response has to be controlled. So that is the structure. That structure is receiving some external excitation here. Means that structure responds to the seismic or wind excitation, and our objectives are whatever are the forces developed in the structure, they need to be controlled. So they can be controlled by different means, but one of the means is active mass damper. So we install the tune mass damper on the top of the structure, and we change its properties in real time. And therefore that tune mass damper is called active tune mass damper or only active mass damper. So this is also a tune mass damper, but its dynamic properties can be changed in real time. For example, there is a mass on top of the structure. So this is the main building, parent structure. On top of that, there is a tune mass damper, and the stiffness and damping of that tune mass damper can be changed in real time. So that becomes an active tune mass damper or AMD. So mathematical represent mean the form of lumped mass modeling. It can be shown like this. The point to be noted here is what are the relative displacements, because the forces developed are dependent on which element we are talking about. If it is a stiffness element, then it is the relative displacement which becomes important. If it is damping, then the relative velocity becomes important, and if it is the acceleration, then it is the absolute, means total acceleration or overall acceleration becomes important. Now this is looking like more of a theoretical discussion. However, in the practice, these kind of active mass dampers have been used in the real life structures, especially in the Japanese area. So there the modeling of the structure again is slightly different from what we have seen in today's class in the beginning. We have a lumped mass matrix, we have a lumped stiffness matrix and damping matrix. It is added with the additional mass of the tune mass damper and corresponding acceleration, displacement, and velocity terms or the vectors. And then you have the external excitation. Now you can either add them here or you can add them as a separate control force. It really doesn't matter. But you have added one additional degree of freedom, which is of course becoming part of your governing differential equation. Please note that as many number of degrees of freedom you have considered, the order of these matrices and these vectors will become as much as that. And if you have additional degree of freedom corresponding to the tune mass damper, that will crop in here. Now, in addition to that, if you have some control force, and again that control force can be directly shown here in the mass stiffness and damping, or it could be separately shown as UU minus. Again, it is only a mathematical way of representing how the different forces are working together. Essentially, what we are talking about is in the time domain at any particular instances, what are the different forces by which the system is in dynamic equilibrium. So without going into this quick mathematical equations, finally we get an equation which looks like this, where you have your masses and stiffness. Again, damping can be appropriately added. It doesn't really matter if you are using some relay or Foucault damping in here. And then you have the external excitation forces acting on the structure. Now, I was talking about the main parent structure, and those equations are developed for the main parent structure, which receives some external input, and we control the response of the structure by some external force. Now, that external force could be through different means, either by external actuators or by putting some device on top of this, which is controlling the response of this structure. That device is controlling the response of the parent structure by some external force being applied on top of it. The parameters of that external device are changed in real time based on what kind of response the structure is giving, because our focus is on controlling the response of the structure. So we have some sensors. Those sensors measure the response of the structure, we give that as a feedback to the controller, and then controller keeps on changing its properties so the response of structures is reduced. So plant is a structure whose dynamic response is to be controlled. Sensors, they measure the response of the structure, and sensors could be anything like accelerometers or velocity sensors. Displacement sensors are relatively not so popular because for that you require a frame of reference in a way. But accelerometers are very, very popular. The control computer and actuator, they are actually a computer and actuator which has to be triggered. Those who work in the laboratories, they would know these terms, that there is some kind of a data acquisition system and there is some actuator. So in a similar manner, that the data acquisition system also has a computer part of it. So there is a computer here, and that computer processes the data received from the sensors and gives the voltage signal or the control command or control input to the actuator, which control the response of the plant, means the original structure. Now in that there are different control algorithms and the way we control this structural response in an active or semi-active system. Again, some very, very fundamental illustrations are given here for the sake of your understanding. The details can be again gone into little later. So on the frequency scale, we can check as to what is change in the frequencies of the structure, and that can be expressed in the form of a transfer function. So transfer function for the plant can be expressed, and we see as to what is the feedback gain in a feedback control algorithm, and then check as to how the transfer function is affected because of the control input given through the feedback gain. Now, in this case, typically here we talk about the controller, and here we are talking about the structure based on whatever is the feedback control we are giving to the structure. We may make the external input excitation part of this, or we can exclude this from without knowing as to what is the external input excitation as part of the control algorithm. Again, there are different ways of this. For example, we can have the external input excitation directly given in the algorithm, and then we are controlling the plant transfer function, and the response is being controlled through the gain signal, that is called the feed forward control. Again, there are different ways we can have this control. I'm not going into greater details of that. However, it is a designer's choice which kind of algorithm to put in, depending on what kind of structure it is, depending on what performance is to be achieved, and whether it is displacement control, velocity control, acceleration control, or in the hierarchy of which out of them are most important to be controlled and which others are not so important or even not to be controlled. So one may think that these are all theoretical discussions and just mathematically oriented and looks very nice on the paper, but it's not so. There are a large number of buildings which are being controlled using some of these advanced devices, but mostly it is there in the seismically advanced countries. So this is one sample list of where the buildings are being controlled by using these kind of active or semi-active kind of devices. When it is being implemented in the devices, these devices are implemented in the real life structure, there are certain practical ways of installing them. So one of the ways is you have an inverted chevron bracing, and then you have the damper placed there, and that damper has the semi-active property. So this is a semi-active hydraulic damper installed there, and mathematically it is represented either in the Maxwell type arrangement of the stiffness and damper or Kelvin-Voigt type of the arrangement, again depending on how the damper has been fabricated. Again, we analyze our conventional multi-degree of freedom system now with the dampers, and then check as to how the change in the semi-active hydraulic damper will overall reduce down the displacement, velocity and acceleration response at these different floors. It means x1, x1 dot, x1 double dot up to x5, x5 dot and x5 double dot, means displacement, velocity and acceleration of these force. That is done by using development of some control algorithms depending on which out of these feed forward or feedback control or open loop or closed loop system that we have used. Excuse me. So I'm showing some of the examples of the real life building where these kind of dampers have been introduced. So it is supposed to be the world's first smart damping and semi-active variable damping structure, which is a Kazima Shizuki building uh, in Japan. So it uses the linear quadratic Gaussian based optimal control force. Now this part, I will quickly go back to the previous slide. So that part is here. What kind of control algorithm has been used? Whether it is probability based or it is frequency dependent, what kind of gains it is using, what kind of input it is receiving, so on and so forth. But when we hear these kind of terms such as linear quadratic Gaussian, it means we are talking about what kind of control algorithm is there, which is controlling the response of the structure by changing the dynamic properties of the devices in real time. The schematic representation of the building can be seen here, the building which I have shown in the previous slide. Now you can see that in the longitudinal, means in the longitudinal direction, in the longer direction, it is quite stiff. So it probably doesn't require any control in that direction. So you can see the dampers are not oriented in that direction. This inverted chevron is in the shorter direction of the building. Obviously, earthquake can hit this building from any side, but it has more vibration oscillations or amplitudes in the transverse direction. So dampers are put in this frame in the transverse direction. One plane of these dampers is here, the other plane in which the dampers are put are here. Now you can see a control computer here, and it is connected with these sensors. Sensors are at different locations. You can see these sensors, and then the connections are made to the control computer. That control computer generates the signal, and then it sends the signal to the semi-active hydraulic damper, as I have shown in the previous slide. And those semi-active hydraulic dampers, they generate the force to control the response of the structures in the transverse direction. I'm calling this as transverse direction, which is the shorter side. In the longitudinal direction, as of now, you do not see any response control as such. Now it is again the choice of structural designer as to which direction response is to be controlled depending on how the overall building layout is. There is another building, Kyobashi Center in Japan, which also has the active mass damper. So this is again a mid-rise building to about 11 floors, and here, apart from the earthquake monitoring, means measuring the earthquake excitation, there is also measurement of wind excitation. So there is a wind vane anemometer installed at the top, and the sensors, they give that signals to the controller, to the computer, to the observation system, in addition to the ground mounted accelerometers, which also gives input to the computer installed here. And that computer again calculates depending on the either ground excitation or the wind excitation, as well as depending on what is the floor response. So you can see the sensors are put on different floors. For example, here you can see at 11th floor there is one sensor, 6th floor there is another sensor, and those sensors are giving data to the computer. It calculates the required force requirement, and it gives it back to the active mass dampers. Now in this particular building, in the Kyobashi Center, there are two units of the active mass damper. One is larger and other is smaller. Again, it depends on either you are interested in controlling the torsional response as well. You can see that this building is torsionally flexible in this direction. This is the longer direction, this is the shorter direction. So these mass dampers are essentially controlling the response in the shorter direction. Longer direction, it is not as much required. But in the shorter direction also, there are two locations at which they are applying the forces, such that they are also in a position to control the torsional response as much as required. So if we have a close look at that, you can see here, this is one active mass damper, this is second active mass damper, this is the same figure from the previous one. And now let us see how the response takes place and how it is controlled. The Active mass damper can have its either stiffness change or damping change. So it is changed by using some driving force or some driving order, and the properties of the actuator is changed in real time. For example, if it is a pendulum type and there is a mass which is hung on top of the structure, and it is connected to a hydraulic damper. The viscosity either can be changed by changing the magnetic properties, having some magnetic particles inside. That's somewhat similar to an MR damper. By measuring the response of the structure, means response of the floor of the structure which is being controlled, and what is the input excitation, and this is the computer controller which gives this feedback signal to the actuator. So this is the schematic of how the active or semi-active control of these active mass dampers happen. However, there might be some fault in the system. For example, there is a power failure and this computer doesn't work. For example, in that case, this actuator will not be having any change in its properties during the actual earthquake excitation. However, mass is still there, it is hung here, so it will have a tendency to oscillate, and it will keep on oscillating when there is some excitation here, and in that process it will still dissipate the energy. It means this tune mass damper is now acting as a passive tune mass damper in absence of the control force. If the control force is there, better, its performance can further be improved. So that is how a semi-active or active control device in our case may also, in our case means in structural engineering, may work as a passive control device, which is essential. Otherwise we may not have designed the parent structure for higher forces when this is deformed and it is not working. How their fabrication looks like when it is installed on the topmost floor. So you can see here the same active mass damper in the Kobayashi center and active mass damper 2. In the previous slide, I have shown them they are installed on the top floor and it is hung here. But practically how they are hung. So there is a steel frame as you can see in this picture, and you can see the cables here, and they are supporting this floor. So floor is being hung using those cables. They are more clear in this picture, and this is the mass. And that mass can be changed. As I have said, carrying the large mass on the top of the floor becomes difficult, so they are carried in the form of some small plates, and then the mass is adjusted by, because mass and stiffness, these two quantities govern the frequency, and that frequency has to be tuned to the frequency in which we are controlling the response. So tuning the frequency means changing, somewhat similar to what we do in our radios. In our radios we have a tuning button, and we change the frequency of our diaphragm of um, the receiver so that there is the same frequency. In the similar manner here, we change the mass and we ensure that whatever is the actual frequency of the parent structure in which we are controlling the response, it is tuned to that frequency. And that tuning can be done by adding some plates or some mass or removing some mass here. So that option is available. Even some kind of steel balls are used to just to play with the mass such that exact frequency can be obtained. Now we know that when we design a structure on paper, we calculate the stiffness and the moment of inertia, its modulus of elasticity is assumed. Modulus of elasticity in case of reinforced concrete structure depends on what is the grade of concrete. But when we actually construct the structure, the grade of concrete may vary. When the grade of concrete is varying, it has it has direct effect on the stiffness matrix. It means frequencies are different. It means modal frequencies are different than what you have actually anticipated in your theoretical design. Also, the cross sections of the elements, if you are designed, let us say, a 9-inch by 15-inch column, but in real life, when it is being constructed, the dimensions may not be exactly 9-inch by 15-inch. There will be some variation. Because of that variation, moment of inertia will change because BD cube by 12 values have changed. Because of that, the frequencies have changed, modal frequencies have changed. So there might be some difference in the theoretically calculated modal frequencies and actual frequencies. Now, when the tune mass damper is to be tuned, it has to be tuned with obviously the actual structure, whatever frequencies it has. So we typically do a ambient vibration or free vibration test on the structure. There is some small shaker is put on that floor, and then the building is given some oscillations, and we measure what are the actual frequencies of the structure, and then we tune the frequency of the tune mass damper to the real life structure, now the frequency which has been evaluated experimentally. So once we do that, and then if we see how the structure is responding practically, and had that tune mass dampers not installed, how the structure would have responded. So you can see there is substantial response reduction in the response of the structure. Here the displacement response has been shown. The thick colored curve shows the controlled response, and the thin colored shows the uncontrolled response. Obviously the uncontrolled is the theoretical one, the controlled one is the practical one, actually observed one, and you can see there is substantial response reduction. But as I have said, in this particular building in the Kyobashi center, there is a possibility of torsional mode, and the torsional mode response is also controlled, and that is shown here on the 11th floor. If that mode would not have been controlled by using this tune mass damper, the torsional displacement would have been as high as this. However, because of those two AMDs put at two different locations, they are also giving some restoring force against the torsional mode of vibration, and because of the torsional modal response has also reduced. So this clearly shows the effectiveness of using the active tune mass dampers on the structures in case of the earthquakes. So likewise, there are different examples. I think I'm shipping over time, but I will quickly rush through the rest of the devices and the practical implementation of those devices in next about 4 to 5 minutes. So this is yet another example building again from Japan, where uh, the semi-active tune mass dampers have been installed. Apart from that, the dampers themselves have different kinds of arrangements for their function. The simple way is you have some mass hung; those are called pendulum type of dampers, for example. There are some kind of translational dampers, as you can see here, where they are put on the top of the structure, connected to that floor with a rigid support, and then there is oscillation of the mass, and the forces are applied on that rigid arm so that the flow response is controlled. This is the practical formation or fabrication of a mass type of tune mass damper. This is the free mass which moves on these rollers here to and fro like this because of its inertial properties, and thereby it applies forces on these framework, and that framework is connected to the floor. You can see the elevation here. So because of the inertia, it moves here on top of these rollers, and this is connected firmly with the building floor, and thereby it applies the forces in the opposite direction. For example, when the building floor is moving in the leftward direction, this mass, because of inertia, is thrown on the backward side, and thereby on the rollers a force is applied on the opposite side. It means on the floor there is a force being applied on the opposite side because of the inertial mass put on the top. Again, we need to calculate how much inertial mass is to be put based on how much force it is applying on the structure in the real time. So in this case, here it is almost 1/400th of the building weight. Means the weight of this trigon, they have named it as trigon, is 1/400th of the building weight. Depending on how much weight we have put and the frequency tuning, we get the response reduction. So that is shown in some of these figures. Sometimes we need to also control the response of the tune mass damper itself. So we may have some additional features incorporated. Even in India also, wherever we have used this tune mass damper, there are control forces applied on the tune mass damper. They can be having another mass damper on top of it to control the response of the tune mass damper itself. So this is a schematic of those kind of active mass dampers in two layers, controlling the response of the primary tune mass damper and the secondary tune mass damper. The primary could be a passive one, and the secondary could be the active one. Excuse me. Pendulum dampers are more popular in the tower type of structures, such as the For example, the Chiba Port Tower in Chiba City, Japan. So it has this kind of damper put in, and the weight of the damper is important in this case. So there are two dampers here having weight 10 tons and 15 tons, and the building height is 125 meters. Please note that they have been uh, incorporated in 1986. So as uh, as back as 1986, they have been using these kind of tune mass dampers. In India, we are yet to use some of these dampers popularly in our, especially in the tall structures. In 1980s, Sydney Tower in Australia, it has a passive pendulum type of tune mass dampers having weight 220 tons, a huge pendulum type of damper. John Hancock Building, it has two tune mass dampers of 300 tons each. The building was constructed in 1997, having height of 244 meters. Instead of installing one damper, we can have additional dampers, and those additional dampers may be able to control the response in the other modes as well. One damper can control response in one vibration mode or model in that particular mode. However, if you are interested in controlling the response in the second mode, for example, in the third mode, for example, then you may have additional damper, and that additional tune mass can be tuned to the frequency in the second mode or in the third mode. So that is called the multiple tune mass damper. Again, there have been some structure where some of these things have been installed. Again, due to paucity of time, I'm rushing to this and how those active mass dampers function in controlling the response in the two orthogonal directions in the planar one. The next category is the hybrid control, where you may have different kinds of dampers put in combination, either semi-active, passive together, or within the passive there are two kinds of passive dampers put together, or within semi-active or active, two different kinds of control systems put together. So that whole thing falls in the category of hybrid control. For example, you have base isolation here, and in addition to that you have dampers installed. So base isolation plus damper, it becomes a hybrid control. Or you have some chevron bracings here. Bracing themselves are helping in the response reduction. In addition, you also have dampers. So likewise, there are different ways in which the hybrid control can be installed. So there are some buildings coming up where some of these devices are being put. This is yet another smart base isolated building with addition of semi-actively controlled variable damping. Q University Sosokon building. This is one of the largest building as well, which is semi-actively controlled. There is another building controlled by using the autonomous decentralized semi-active smart damping. This is again a very advanced kind of damper installed in this building in Gifu in Japan. Here the autonomous decentralized semi-active control is such that you are controlling the response at different locations by using different algorithms themselves. So it is decentralized. There is not just one single computer which is controlling the response of the entire system. No, there are decentralized different kinds of control algorithms at different places. So this is how the semi-active damper in real life looks like. And in this particular building, they have used the switching oil damper with built-in controller. And this decentralized algorithm is very fascinating. Actually, if you can see here, this is the main structure, and there are three control algorithms: the innermost loop, the middle loop, and the outermost loop. And you have different actuators in each one of them, which are controlling the response of the structure. And the sensors are giving feedback to the control computer in all the three different algorithms. So this has been already practically implemented. These are the force deformation loop obtained there. So with that, I will quickly conclude my presentation today. So structures are exposed to different kinds of dynamic excitation, either during the ambient conditions or external forcing function coming either from base excitation, which is earthquake, or mass excitation, which is wind. Again, wind can be the extreme winds or the ambient winds affecting the serviceability of the structure. So vibrations can be induced from any one of them. that vibration response can be controlled, can be reduced, can be abated by different kinds of devices. And these are some state of the art advanced devices or equipments which can be installed in the structure, which will not only improve the safety of the structure during these extreme events, but also they can be used for controlling the ambient vibrations or improving the serviceability of the structures. Particularly, for example, in the long span bridges or tall structures, ambient oscillation control itself becomes important. So that can be achieved by using these kind of devices. The technological know-how of these vibration control or dynamic response control devices is readily available, particularly for the earthquake resistant design of structures. So with these concluding remarks, I end my presentation. But before doing that, I again thank Professor Aruna Rao for inviting me to interact with you. I'm thankful to the faculty members of UIT RGPV. And of course, thank you very much for all of you to patiently hearing me for the last 2 hours. I will be glad to take up any questions that you may have. Thank you so much.
Yeah, thank you very much, sir. Thank you very much for in detail you have elaborated the various vibration control systems which are used for the earthquake resistant design. Thank you very much. I request participants to please ask if you have some queries or you can type it in chat box also. Any queries?
Yes, ma'am. Can I ask the
Yes,
question?
yes, sir. Please.
Okay, I am from the architectural faculty. So we are referring the IIT Kanpur earthquake tips. So any sir has excellently told us regarding the passive, semi-active, and active parameters to withstand the earthquake forces. But the question is for the masses when the people are not going to afford the cost of the construction. Any kind of planning and designing features we should know so that we can teach to the students because just we are referring the earthquake tips and as per the syllabus we have found. So any kind of solution or any kind of what suggestions sir could have given us so it will
Yeah,
be more
yeah.
better.
Yeah, so it is a very pertinent and valid point, sir, that you have raised. In tomorrow's presentation, I will be talking about the practical implementation of one of these devices in the Indian context, and which is, in a sense, cost effective because specifically in India, we are very much cost conscious. So,
Yeah,
out of these different devices that I have talked about, I have just given glimpse of all kinds of devices, most of these
yeah,
devices.
yeah, yeah,
Again,
yeah, sir.
just to inform this gathering, we teach this course for one full semester of just response control of the structure. So you can imagine the vastness of this whole course or this whole knowledge base, which I had covered only within 2 hours. So
Yeah, yeah,
out of this, in the Indian context, specifically seeing the cost effectiveness or whether we can afford these devices and still ensure that the performance of the structure is ensured, not all these devices are applicable. Only some of these devices are applicable in our context if we are very cost conscious. For example, in India, we have been already using viscous dampers, friction dampers, and base isolation systems. So these are the
yeah.
three devices which are cost effective as well as they are readily available in the Indian context. We have know how to use them and construct the structures out of that. Tomorrow I will show one of those examples of how we have installed one friction type of isolation system to control the response of a structure. But there are other examples where we have worked. For example, in Apollo Hospital in Delhi, they have used viscous dampers. In the air traffic control administrative building at Indira Gandhi International Airport, they have used viscous dampers to control the response of the structure. So these are some of the passive control devices which are used in India for controlling the
Okay,
cyclone and wind response of the structure. In case of air traffic tower control in the Indira Gandhi Airport, they have used tune mast damper. As well as some residential towers, tall buildings in Mumbai, they are using the viscous dampers.
okay, ma'am. Thank you, sir. Thank you.
Yeah, my pleasure.
Any other queries, please? Any other queries? Okay, so thank you very much, sir.
My pleasure.
Thank you very much, sir, for giving a detailed description of vibration, various vibration control systems. And we will have tomorrow also sir's session at 10 a.m. where he will be elaborating the various case studies related to the use of these vibration systems in India. Thank you very much, sir.
Thank you.
Dear participants, shortly we will start with session 7. So please remain joined to this link